Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So I want you to imagine you are standing on a beach.
Okay, a beach.
Yeah. But you're looking at this vast, dark ocean. You can hear the rhythm of the waves, right? They're crashing against the shoreline.
Sounds relaxing so far.
Right, and you can feel this heavy, really dense atmosphere just pressing against you. And there's rain falling from the sky. It's drumming against the ground.
Okay, so a stormy day on the coast?
Exactly. It sounds exactly like a stormy day on the coast here on Earth.
Yeah.
But, and this is the huge catch, if you were to, say, reach down and scoop up a handful of that ocean, or even just let a raindrop hit your tongue, the thermal shock would instantly flash freeze your entire cellular structure.
Oh, wow. Yeah, that is a profoundly unsettling image to visualize.
Because that rain, those rivers and that whole vast crashing ocean, they aren't made of water at all.
No, they absolutely are not.
They're made of liquid methane.
Right, because you're standing on the surface of Titan.
Exactly. Saturn's largest moon.
It's wild. You have all the mechanical familiarity of a hydrological cycle, like the rain and the rivers, but the chemistry is entirely, completely alien.
Completely alien. Because the ambient temperature on this beach, even during the absolute peak of a sunny day, is hovering right around 90 Kelvin.
Which is about negative 180 degrees Celsius.
Negative 180 degrees Celsius. I mean, that is a thermodynamic regime where water, as we understand it, it basically ceases to be a solvent. It essentially becomes bedrock.
Yeah, exactly. At those extreme temperatures, water ice has the tensile strength of silicate rock.
Right. It's literally forming the mountains.
It forms the mountains, the valleys. The actual crust of the moon itself is water ice.
Which is just crazy to think about.
It really is. On Titan, water ice is the geology. But what makes Titan so incredibly captivating to planetary scientists and astrobiologists especially is that despite being this cryogenic world wrapped in a thick nitrogen atmosphere, it is arguably the most Earth-like planetary body in our entire solar system.
Which feels like, I don't know, an ultimate paradox, right?
It really does.
Because when people hear Earth-like, your immediate association is, well, a temperate climate, maybe some green vegetation and liquid water.
Sure, the classic habitable zone stuff.
Right. But in planetary physics, Earth-like actually denotes something else. It denotes an active, phase-transitioning fluid cycle.
Yes. The liquid methane and ethane on Titan, they actually flow through these deeply carved river valleys.
They pool into massive lakes.
Massive lakes and seas, mostly up in the northern hemisphere. And they evaporate into that nitrogen atmosphere, they form complex cloud systems, and then they precipitate back down to the surface.
It's a perfect kinetic mirror of Earth's water cycle. It's just operating with, non-polar hydrocarbons instead of highly polar H2O.
Exactly. And wherever you have an active fluid cycle like that, you automatically have a dynamic non-equilibrium environment.
Right. The chemicals aren't just sitting there.
No, the chemical constituents are not just frozen in a static matrix. They are actively mixing, they're interacting, dissolving, and precipitating.
And that inherent kinetic energy, that constant chemical mixing, leads us directly to the most profound question we can ask about our cosmic neighborhood.
The big one.
The big one. The question that has honestly driven decades of planetary exploration. If Titan possesses a meteorological cycle that's so beautifully complex and so mechanically similar to ours, could exotic low-temperature forms of life have evolved there?
Right.
So today, we're setting out to trace the trajectory of that exact question. We're following the scientific journey from the theoretical mathematics of molecular simulations all the way to the freezing laboratories of advanced cryoengineering.
It's a fascinating journey.
It really is.
Yeah.
Because we are looking at the foundational problem of astrobiology. If life did evolve in an environment where the biological rules are written in liquid methane instead of water, how do we even begin to conceptualize that, let alone test for it?
It is the ultimate puzzle in physical chemistry, because to understand how life could physically structure itself in liquid methane, we first have to really understand the thermodynamic packaging of life here on Earth.
Right, the basics.
Exactly. And more importantly, why that specific Earth packaging entirely fails on a moon like Titan. Because biological life, at its very core, it requires a localized gradient. It requires a boundary.
A container.
Yes, a container.
So let's unpack the mechanics of that boundary for a second. On Earth, the fundamental container of biology is the cell.
Right?
And the wall of that container is the lipid bilayer membrane. But it's not just a passive wall, right? Its formation is actually driven by the specific chemical properties of water.
It is entirely dependent on water. Water is a highly polar molecule.
Meaning it has a positive end and a negative end.
Exactly, like a little magnet. Now, the lipids that make up our cell membranes, they are amphiphilic.
Amphiphilic.
Yeah, which basically means they have a hydrophilic or water-loving head that is polar and a hydrophobic or water-fearing tail that is nonpolar.
Okay, so one end loves water, the other end hates it.
Right. So when you drop these lipids into water, the thermodynamics of the system just take over automatically. To minimize the free energy of the system and maximize the entropy of the surrounding water molecules, the lipids spontaneously self-assemble.
They just organize themselves.
They do. The hydrophobic tails tuck inward, away from the water, and the hydrophilic heads face outward towards the water, and boom, they form a stable, flexible bilayer.
It's a brilliant self-organizing system. It's totally driven by that hydrophobic effect.
Yes.
So the cell membrane is essentially this localized zone of low entropy that allows highly organized, very specific chemistry, which is what we call life, to happen on the inside.
Right. It protects the internal machinery.
Because otherwise, those delicate chemical pathways would just simply diffuse away into the broader chaotic ocean, right?
Exactly. Without the container, there's no life. But here is the massive problem. If you take that Earth-evolved lipid bilayer and transport it to Titan's hydrocarbon lakes,
Oh, boy.
the physics violently rebel.
Violently?
Yeah, because liquid methane is a non-polar solvent. It has a dielectric constant of about 1.7.
Compared to water, which is what?
Water is around 80.
Oh, wow. Okay, that's a huge difference.
It's massive. So if you put an Earth lipid into liquid methane, the hydrophobic effect is completely reversed.
Wait, really? Reverse?
Yes. The tails would actually want to interact with the methane, and the polar heads would clump together to escape it.
So the entire structure would theoretically turn inside out.
Theoretically, yes, but practically. At 90 Kelvin, the thermodynamic energy is so incredibly low that the long carbon chains of Earth lipids would simply freeze into a rigid crystalline solid.
They just snap.
They would shatter. An Earth-style membrane literally cannot exist on Titan.
And for decades, that was just a massive conceptual roadblock for astrobiologists, right?
A huge one. I mean, how do you compartmentalize life without a polar solvent to drive the assembly of a flexible membrane?
Which brings us to this major paradigm shift that happened back in 2015. I want to look really closely at the research that came out of Cornell University during that time, because it seemed to just completely bypass this polarity problem altogether.
It was a very elegant approach.
Yeah, because the researchers didn't look for Earth-like lipids. They turned to advanced computational modeling to search for a completely new type of membrane that would be native to Titan's chemistry.
Right. The Cornell team focused on a very specific, relatively simple molecule called acrylonitrile.
Acrylonitrile.
Yes, it's a vinyl group linked to a nitrile, which is essentially a type of cyanide.
Cyanide, which obviously is highly toxic to biological life down here on Earth.
Extremely toxic.
But in the context of Titan, it's just like a standard component of the atmospheric photochemistry.
Precisely. We know from the Cassini-Huygens mission data that acrylonitrile forms naturally in Titan's upper atmosphere. It happens through the ultraviolet irradiation of nitrogen and methane.
So it's already there. It's a confirmed native ingredient.
It exists there in abundance. So the Cornell researchers hypothesized that as this acrylonitrile rains down into the surface lakes, it might actually possess the right geometric and energetic properties to form a membrane on its own.
But obviously they couldn't just, fly out to Titan with a microscope to check.
No, they had to simulate it.
Right. And when we say simulate, for anyone listening, we aren't talking about drawing a neat little 3D model on a screen.
Oh, absolutely not.
We are talking about molecular dynamics.
Yep.
So for the listener who might be a little fuzzy on how a molecular dynamics simulation actually operates under the hood, how are these physicists actually mapping the behavior of individual molecules?
So molecular dynamics, or MD, is essentially classical Newtonian mechanics, but scaled all the way down to the atomic level.
Okay.
In these simulations, you basically construct a virtual box. and you fill it with thousands of solvent molecules, in this specific case, liquid methane. And then you add your target molecules, the acrylonitrile. You have to meticulously define the physical parameters of every single atom, its mass, its partial charge, and the van der Waals forces it exerts.
So you're defining the specific force field for everything in the box.
Yes, you apply a force field, which is really just a set of mathematical functions that describe the potential energy of the entire system. Then you let the supercomputer calculate the trajectory of every single atom over time.
It's tracking everything bumping into everything else.
Exactly, taking into account how they naturally repel and attract each other. You integrate Newton's equations of motion in incredibly tiny time steps, usually on the order of femtoseconds.
Wait, a femtosecond? That's what, 1/4,000th of a second?
1/4,000th of a second, yes. So you calculate the forces, you move the atoms a fraction of a nanometer, and then you recalculate the whole thing again.
The computational load for that must be staggering. I mean, tracking the multi-body interactions of tens of thousands of atoms, femtosecond by femtosecond, just to see if they bump into each other and stick.
It requires massive parallel supercomputing. It takes weeks, sometimes months of processing time.
Wow.
But the output of that immense computational effort back in 2015 was nothing short of revolutionary for astrobiology.
Because of what the molecules did.
Right. When the Cornell team ran the MD simulations at the simulated Titan temperatures and pressures, the acrylonitrile molecules spontaneously self-assembled.
They actually stuck together.
They linked together to form a highly stable, hollow, spherical membrane.
And this is the theoretical structure that they dubbed the azotosome.
The azotosome, exactly. Azoto referring to the nitrogen in the cyanide group, and some deriving from the Greek word for body, much like a liposome here on Earth.
And structurally, the simulation showed that these azotosomes possessed a flexibility and a stability that was remarkably analogous to Earth's lipid bilayers.
Which is incredible.
Right. Despite being made of toxic cyanide and floating in sub-zero methane, they acted like our cells.
Yes. The simulation suggested that the nitrogen-rich ends of the acrylonitrile molecules would group together to form a protective inner and outer layer.
Okay.
And the carbon-rich tails would be sandwiched safely in the middle. It was this beautifully elegant, mathematically validated model of a truly alien cell wall.
I mean, you could imagine the shockwaves this sent through the exobiology community at the time.
Oh, it was huge.
Because think about it. If the fundamental building blocks for a functional cellular container are constantly raining from the sky into a liquid ocean, naturally self-assembling into these protective spheres,
Suddenly, Titan looks very different.
it totally transitions from just a fascinating cryogenic rock to a prime candidate for a thriving, exotic biosphere. It implies that the genesis of biological structure is just an inevitable thermodynamic consequence of the local chemistry.
It completely dictated the direction of astrobiological discourse for a half-decade. It influenced grant proposals, the conceptual design of future lander missions like the Dragonfly mission, and how planetary chemists even interpreted atmospheric data.
The azotosome just became the accepted theoretical framework for Titanian biology.
It did, but
There's always a but in science.
always. But the inherent vulnerability of relying solely on molecular dynamics is that it is fundamentally a classical approximation.
Right.
It basically treats atoms as interacting spheres connected by springs.
Which is a simplification.
A huge simplification. And while that is incredibly useful for modeling large-scale conformational changes over time, it leaves a significant blind spot when it comes to the fundamental energy states that are actually holding those molecules together.
Which is exactly what prompted a really profound reevaluation of the azotosome model a few years later.
Yes. The limitations of those classical force fields led a completely separate group of theoretical physicists at Chalmers University of Technology in Sweden to approach the problem again.
This was in 2020, right?
2020, yes. And they approached it from a fundamentally different mathematical paradigm. They didn't use molecular dynamics at all.
So what did they use?
They utilized quantum mechanical calculations, specifically something called density functional theory, or DFT.
Okay, so if you're listening and wondering why a shift from a molecular model to a quantum model would completely upend a 5-year-old consensus, it really comes down to what the simulation is actually seeing, right?
Exactly. As we said, molecular dynamics ignores the electrons entirely. It just assumes the chemical bonds are predefined and perfectly stable.
It's just looking at the balls and springs.
Right. But quantum mechanics, and specifically density functional theory, looks at the electron density of the entire system. It calculates the ground state energy of the molecules by meticulously mapping how the electron clouds interact, how they overlap, and how they repel.
So it's not looking at the system kinematically.
No, it looks at it thermodynamically.
It's calculating the precise energy budget required for these molecules to exist in a specific geometry.
Exactly. And this is where the extreme environment of Titan becomes the absolutely critical variable, the intense cold. At 90 Kelvin, the ambient thermal energy, what physicists refer to as the KT value, is exceptionally low.
Okay, so there's barely any free energy floating around to power things.
Right. So chemical reactions and structural assemblies that require an input of energy to overcome a barrier simply cannot occur because the environment just cannot provide that initial thermal kick.
So when the Chalmers team applied their quantum calculations to the specific geometry of the azotosome, what did the thermodynamics actually reveal?
It revealed that the azotosome was thermodynamically unstable.
Unstable.
Yes. The older MD simulations showed a plausible geometric arrangement, sure, but the quantum mechanics calculated the actual free energy of formation. And it turns out to force acrylonitrile molecules to align into a curved spherical shape requires introducing severe mechanical strain into the molecular lattice.
Okay, so it's akin to trying to, I don't know, bend a thick sheet of cold-rolled steel into a tight cylinder without using a blowtorch.
That's an excellent way to put it.
Right. Because geometrically, on paper, you can draw a picture of the steel formed into a perfect pipe. You can visualize exactly how the edges would meet.
Sure, you can draw it.
But practically, in the real world, without a massive input of thermal energy to soften the metal, the sheer physical resistance of the material will prevent it from curving. The energy barrier is just insurmountable.
That is an incredibly apt analogy. The thermal energy required to bend the acrylonitrile lattice into a sphere and then maintain that curvature is significantly higher than the ambient energy available in liquid methane at negative 180 degrees Celsius.
It just doesn't have the heat to bend.
Exactly. Furthermore, the quantum calculations showed that the acrylonitrile molecules would strongly prefer to crystallize into a solid block rather than form a hollow shell.
Because nature is lazy, right?
Nature always favors the lowest possible energy state, and the azotosome was simply too energetically expensive to exist.
Which honestly places the scientific community in a fascinating gridlock.
Oh, a total gridlock.
Because you have two highly respected groups of theorists, both using state-of-the-art computational tools, but they are arriving at mutually exclusive conclusions based on the parameters of their respective mathematical frameworks.
Right. The 2015 molecular dynamics model says the azotosome is a natural, highly dynamic structure.
And then the 2020 quantum mechanical model comes in and says the azotosome is literally an energetic impossibility.
And the problem is theoretical physics alone cannot resolve that contradiction.
Because it's just math arguing with math at that point.
Exactly. A model, no matter how mathematically rigorous it is ultimately just an abstraction of reality. When you have two conflicting abstractions, the only way forward is empirical observation.
You have to step out of the computer.
You have to remove the abstraction entirely.
You have to actually attempt to build the alien membrane in the physical world.
Yes.
Which, sounds conceptually straightforward, like let's just mix it in a beaker. But practically, how do you synthesize a piece of Titan in a laboratory on Earth without the entire apparatus either freezing solid or just exploding?
The engineering required to simulate Titan's surface conditions is staggering. And this brings us to the pivotal empirical research conducted by Tuan Vu and Robert Hodis.
Out at NASA's Jet Propulsion Laboratory.
Yes, JPL. To finally settle this theoretical debate, they engineered a specialized cryostat.
A cryostat.
Yeah, a highly advanced cryogenic chamber that is capable of holding precise mixtures of volatile hydrocarbons at a stable 90 Kelvin.
The thermal management for something like that alone is a marvel. I imagine you can't just, drop the temperature, flip a switch, and walk away. Maintaining a stable liquid phase of ethane and methane has to require a really delicate equilibrium.
It requires extreme precision. The cryostat is typically cooled using closed-loop liquid nitrogen lines. But you also have to isolate the chamber completely from ambient room temperature, which requires high vacuum jacketing around the experimental cell.
Like a really, really intense thermos.
Exactly like a thermos. It eliminates convective and conductive heat transfer. inside this highly controlled thermodynamic void, Vu and Hodes prepared solutions of acrylonitrile mixed with ethane and then separately with methane.
Precisely mimicking the solvent profile of Titan's actual lakes.
Exactly.
And once the mixture is stabilized at 90 Kelvin, the critical challenge becomes observation. Because if you are trying to determine whether these molecules are forming flexible membranes or rigid crystals, you have to actually look at them.
Right, you need to see what's happening.
But you're dealing with a sealed, vacuum-jacketed pressure vessel containing cryogenic fluids. Any traditional optical method, like a normal microscope, is severely compromised by thermal gradients or frosting on the glass.
You can't just peer through it.
Right. So how do they actually see the molecular structure without disturbing that perfect cryogenic equilibrium?
You utilize non-invasive, high-precision thermodynamic and optical sensors. The JPL team employed two highly advanced techniques for this. The first was differential scanning calorimetry, or DSC.
DSC is a fascinating technique because it essentially uses heat, or rather the lack thereof, as a diagnostic tool.
Yeah.
How does it isolate the structural changes of the acrylonitrile?
So DSC measures the exact amount of heat required to increase the temperature of an experimental sample compared to a chemically inert reference material.
Okay, so you have a baseline.
Right. As you slowly vary the temperature of the cryostat, you carefully monitor the heat flow. When molecules undergo phase transition, for example, when they self-assemble into a structure or lock into a crystal lattice, that process is either exothermic or endothermic.
Meaning it either releases latent heat into the system or it absorbs it.
Exactly.
So by plotting the heat capacity curve, you can identify exactly when and how the structural geometry is altering. It's conceptually really similar to metallurgy.
Oh, how so?
Well, if an engineer wants to determine the precise carbon composition of a steel alloy, they don't necessarily look at it under a microscope. They chart its specific heat capacity curve as it warms up. The precise temperatures where the alloy absorbs sudden spikes of thermal energy reveal the internal crystalline phase changes.
That's a perfect parallel. DSC is doing exactly that, but at the molecular level in cryogenic methane.
Right.
The thermal fingerprint reveals the onset of molecular assembly. But there's a catch. DSC only tells you that a structure formed and at what energy level.
It doesn't tell you what shape it is.
No. To determine the actual geometry of the structure, to see if it's a spherical azotosome or a solid block of crystal, they needed a second technique. They utilized Raman microscopy.
Which requires bouncing high-intensity lasers off the samples inside the cryostat.
Yes. To accomplish this, the cryostat is fitted with highly specialized sapphire viewing ports.
Sapphire.
Yeah, sapphire is incredibly strong, can easily withstand the intense thermal shock, and crucially, it is optically transparent to the specific laser wavelengths they used.
Okay, so the laser goes through the sapphire.
Right. Now, Raman spectroscopy relies on the inelastic scattering of photons. When the laser light penetrates the liquid methane and strikes the acrylonitrile molecules, the vast majority of the photons just bounce back elastically without changing energy at all.
And that's called Rayleigh scattering, right?
Exactly, Rayleigh scattering.
But a tiny fraction of those photons actually interact with the vibrational modes of the chemical bonds themselves.
Yes, and this is the magic of the technique. Molecules are not static. Their chemical bonds are constantly vibrating and rotating. In solid-state physics, these quantized modes of vibrations are called phonons.
Phonon.
Yeah. When a laser photon hits a vibrating bond, it either transfers a minuscule amount of energy to the bond, or it absorbs a tiny amount of energy from it. Consequently, the photon that scatters back out to the sensor has a slightly shifted wavelength.
A different color.
A slightly different color. This is known as the Raman shift.
And because the vibrational frequency of a carbon-nitrogen bond inside a flexible hollow membrane is mathematically distinct from the vibrational frequency of that exact same bond locked inside a rigid crystal.
The spectral shift of the laser light gives you an exact, real-time topological map of the molecular architecture.
That is just insanely clever. It provides undeniable spectroscopic proof of the molecular configuration.
It does. So armed with the DSC thermal data and the Raman spectral mapping, the JPL team peered into their simulated Titan lakes.
The moment of truth.
They were looking for the distinct, dynamic molecular signatures of the azotosome that those 2015 molecular dynamics models had promised.
And what did the empirical data actually reveal about the thermodynamic reality of liquid methane?
The data was unequivocal. The experimental results heavily validated the 2020 Chalmers theoretical study.
The quantum mechanical models were correct.
They were completely correct. The acrylonitrile molecules did not assemble into spherical azotosomes. Not even close. When introduced into the liquid ethane mixture, the Raman spectroscopy revealed that the acrylonitrile and ethane molecules interacted to form a highly stable molecular co-crystal.
Okay, let's clarify the exact nature of a co-crystal in this context, because this really represents the definitive end of the azotosome hypothesis. Like, a co-crystal isn't just like a frozen clump of molecules stuck together randomly.
No, a co-crystal is a highly ordered, single-phase crystalline material. It's composed of two or more different molecules within the exact same lattice.
Okay.
In this case, the acrylonitrile and the ethane are driven by weak intermolecular forces, likely van der Waals forces, and maybe some weak hydrogen bonding or dipole interactions to lock together into a rigid, repeating, three-dimensional geometric grid.
And the fundamental distinction between a crystalline grid and a cellular membrane is the difference between a living architecture and a static one. Because a membrane, like a lipid bilayer, relies on lateral fluidity. The molecules align to form a barrier, sure, but they are constantly moving, slipping past one another.
They're fluid.
That fluidity is what allows the cell membrane to actually function. It allows proteins to embed themselves in the wall. It allows for the formation of pores. It allows the cell to divide, to stretch, and to regulate osmotic pressure.
But a co-crystal has zero lateral diffusion. The molecules are thermodynamically trapped in their lattice positions. They are frozen in place.
Right.
You simply cannot construct a functioning, dynamic biological boundary out of a solid crystal. It is structurally dead.
Wow.
Furthermore, the experimental results involving the liquid methane mixture were even more definitive.
Because methane is the primary constituent of Titan's northern seas.
Exactly. And in the methane mixture, the acrylonitrile showed virtually no interaction at all.
Wait, really? None?
None. It is practically insoluble in liquid methane at 90 Kelvin. And think about it. If a molecule cannot dissolve into the solvent, it cannot freely interact, and it certainly cannot dynamically self-assemble into a complex membrane.
It just sinks to the bottom.
The acrylonitrile merely precipitated out. The assembly of azotosomes was completely non-existent.
It's a brilliant piece of experimental physics. But it really does leave a lingering question regarding the initial modeling. I mean, how could the initial 2015 molecular dynamics simulation, which, as we discussed, utilized highly sophisticated force fields and really rigorous classical mechanics, produce a result that was so fundamentally disconnected from physical reality?
It's a great question, and it highlights a classic vulnerability in computational chemistry. It's known as falling into a local energy minimum.
A local minimum?
Yeah. The simulation likely found a geometric arrangement, the spherical azotosome, that represented a localized stable state within the specific constraints of its classical force field.
Okay, so the math worked, but only inside the box they drew.
Exactly. However, because it couldn't calculate the complex electron-cloud interactions or the massive entropic penalties of creating that curvature at cryogenic temperatures, it couldn't see that the global thermodynamic minimum, the true state that nature will invariably seek out, was the solid crystal.
The simulation was mathematically sound within its own parameters, but its parameters were just an incomplete map of the territory.
That's beautifully said, yes.
Which is the harsh beauty of the scientific method, right?
Yeah.
The empirical data shatters the elegant theory. But this brings us to the broader, perhaps slightly daunting implications of these JPR findings.
The big picture.
Right, because if acrylonitrile completely fails to form membranes, if it just ignores methane and locks into lifeless crystals with ethane, does this effectively close the door on the possibility of complex, compartmentalized biology existing in Titan's oceans? Are we just looking at a sterile moon?
It doesn't close the door on biology. Not at all. It forcefully closes the door on our anthropocentric assumptions about biology. The ultimate consensus among planetary chemists analyzing this data is not that Titan is sterile, but that we have been conceptually constrained by our own evolutionary history.
We've been projecting the structural blueprints of a water-based biosphere onto a methane-based environment.
Precisely. Because every single biological entity on Earth utilizes a spherical amphiphilic membrane to define its boundaries, we just naturally assume that life on Titan must possess an analogous structure.
We were looking for a cryogenic equivalent of a liposome.
We were. But this experiment categorically proves that the thermodynamic rules of liquid methane vehemently oppose that specific architecture. Researchers are now concluding that despite their absolute ubiquity in aqueous environments like Earth, spherical membranes are likely not a prerequisite for functional biological organization in alternative solvents.
Which represents a massive conceptual leap.
Huge.
If you discard the discrete enclosing membrane, the container, how does a complex chemical system maintain the necessary non-equilibrium state? How does it prevent the dilution of its internal chemistry into the surrounding ocean?
That is the absolute frontier of theoretical astrobiology right now. If life exists in liquid methane, it must rely on entirely different physicochemical mechanisms to maintain spatial organization. We have to look beyond the vesicle.
So what are the alternatives?
Well, perhaps it relies on liquid phase separation. This is similar to how certain membraneless organelles operate within human cells via complex coacervation.
Like droplets within droplets.
Exactly. Or perhaps biology on Titan doesn't float freely in the bulk liquid at all.
You're suggesting life situated at the boundary layers.
Exactly. Interfacial life.
Oh, wow.
Complex, self-catalyzing chemical networks could exist exclusively at the solid-liquid interface. Imagine them draped across the crystalline water ice bedrock or clinging to mineral deposits at the bottom of the methane seas.
So the rock itself acts as the anchor.
The solid surface provides the necessary structural scaffolding and the concentration gradient. It completely eliminates the need for a discrete cellular envelope. The biology wouldn't exist as isolated cells floating around, but as an integrated, self-sustaining chemical pattern propagating directly across the geology.
It forces a complete redefinition of the physical parameters of a living organism.
It really does.
And when we contextualize this paradigm shift within the broader scope of current exobiological research, we uncover a really profound duality in how the universe handles the chemistry of life.
The contrast is amazing.
Because while the physics of Titan is aggressively rejecting the architectural rules of Earth life, deep space exploration is simultaneously proving that the raw chemical ingredients of Earth life are surprisingly common.
Yes, the parallels with recent cosmochemical discoveries are striking. Look at the data retrieved from the Hayabusa 2 mission.
The one that analyzed pristine samples from the near-Earth asteroid Ryugu.
Right. While astrobiologists are realizing that Titan cannot support Earth-like structural membranes, the geochemical analysis of those Ryugu samples revealed something extraordinary.
They identified the presence of uracil,
Yeah.
which is one of the 4 key nucleobases comprising RNA. And they found it alongside niacin and various amino acids.
Exactly. The fundamental chemical letters of Earth's genetic code, the precise nitrogenous bases that drive our biology, were found embedded in a carbonaceous chondrite asteroid.
Synthesized out in the cold.
Synthesized purely through abiotic photochemistry in the freezing vacuum of the early solar nebula.
It presents an incredibly complex picture of cosmic chemical evolution. Because, think about it, the universe appears to effortlessly synthesize the precise molecular building blocks of aqueous life, the uracil, the amino acids, in the harsh radiation of deep space.
It freely distributes the familiar ingredients.
Yet, when you attempt to construct a functioning biological system within a complex planetary fluid cycle like Titan's, the environment absolutely refuses to utilize those familiar architectural blueprints.
It's a stubborn environment.
It provides the building blocks of DNA in a vacuum, but it demands a completely unrecognizable structural paradigm in a methane ocean.
It suggests that the emergence of complex chemistry is a universal thermodynamic imperative. But the specific morphology of that chemistry is entirely solvent-dependent.
Right.
The biological structures we observe on Earth are not the universal standard. They are simply the inevitable consequence of utilizing liquid water as a solvent. If a biosphere exists in liquid methane, its structural mechanisms will be an inevitable consequence of that specific cryogenic nonpolar environment.
So the JPL experiment fundamentally serves as a profound liberation of our scientific imagination.
A liberation, I like that.
Because by definitively proving that the azotosome hypothesis collapses into rigid co-crystals, Vu and Hodis dismantled a beautifully distracting illusion. They proved that attempting to map Earth's structural biology onto Titan's chemistry is a thermodynamic dead end, which forces the astrobiology community to aggressively expand its theoretical horizons.
It is the essence of empirical progress. We followed a logical hypothesis, grounded in molecular dynamics, to its physical breaking point. And the resulting collision with quantum thermodynamics and cryogenic reality has cleared the path for genuinely novel conceptual frameworks.
It is just a remarkable scientific arc to trace. We began with the mesmerizing observation of Titan's fluid dynamics, a weather cycle mirroring our own. yet driven by sub-zero hydrocarbons.
Right.
That mechanical familiarity inspired theoretical chemists to utilize advanced force field models to construct the azotosome, which was this tantalizing vision of alien cell membranes assembling in alien seas. And for 5 years, that model defined the parameters of the search for life.
Until the deeper resolution of density functional theory highlighted the massive entropic penalties of such structures.
Right, culminating in the extraordinary technical achievement at JPL. Engineers building a vacuum-jacketed, liquid nitrogen-cooled cryostat just to simulate the alien ocean, and utilizing the inelastic scattering of laser photons to watch those theoretical membranes fail to form, locking instead into solid, lifeless lattices.
It is a masterclass in how empirical physics relentlessly corrects theoretical modeling.
Resolving the azotosome debate, but fundamentally opening the door to a much richer, albeit vastly more complex, understanding of potential alien biochemistries.
Exactly.
Which leaves us with a profound conceptual challenge to end on. Because if you consider the sheer diversity of biological forms on our own planet, from microscopic extremophiles and deep-sea vents, to massive sequoia trees, from the neurology of a cephalopod to the structure of your own hands, every single iteration of that immense biological complexity is predicated on the exact same fundamental mechanism.
The container.
A polar lipid membrane encapsulating an aqueous solution. The discrete container is the foundational law of biology as we know it. But as the data from Titan forces us to abandon that law, we must attempt to visualize a biology that operates without containers.
Which is incredibly hard to picture.
We must imagine self-replicating, energy-harvesting chemical networks that do not exist as distinct entities floating in a void, but as dynamic, localized thermodynamic processes interwoven directly into the extreme environment.
Integrated into the world itself.
If a biosphere is operating within the cryogenic methane lakes of Titan, it won't just look alien to us. It will challenge the very definition of what constitutes an organism, blurring the line between the living chemistry and the planetary geology it resides upon. So think back to that image of standing on that cryogenic beach, the negative 180-degree winds driving waves of liquid methane against mountains of rock-hard water ice. We used to peer into that dark ocean searching for the familiar shape of a cell, a microscopic container of life. Now, stripped of our earthbound assumptions by the rigorous mechanics of thermodynamic physics, we must look at that incredibly complex, swirling chemical environment and ask a far more daunting question. Could the ocean itself be the architecture of life?